Hey there, AI explorers. Have you ever struggled with a machine learning model that just won't give you accurate predictions? Well, what if I told you that you don't need just one model? What if you could combine multiple models to supercharge your accuracy? Welcome to the power of Ensemble Learning. Today, we're going to break down bagging, boosting, and stacking, but in the most beginner-friendly way possible. By the end of this video, you'll be able to apply these techniques like a pro. And the best part? We'll run real hands-on examples together. Ready? Let's go. Okay, let's start with the basics. What is ensemble learning? Let's imagine you're on a Who Wants to Be a Millionaire game show. You're stuck on a tough question. What do? You use the audience poll lifeline. Why? Because a group of people collectively will make a more accurate decision than one person alone. That's exactly what happens in ensemble learning. Instead of relying on a single model, we combine multiple models to make better predictions. Think of it as a team of experts versus one random guess. Now let's look into the 3 techniques in ensemble learning. First, bagging, or the power of voting. Bagging stands for bootstrap aggregating, and it's like asking multiple experts for advice and then averaging their opinions. Imagine you have 100 judges rating a talent show. Instead of relying on just one biased judge, you take the average score from all 100. That makes the result more stable and less likely to overfit. Now, why does bagging work? Well, the answer to this is very simple, as it reduces overfitting, increases accuracy, and works great with decision trees. Cool, right? But now, what if we improve weak models step by step? That's where boosting comes in. Boosting, or we can say learn from mistakes. Boosting is like teaching a student for an exam. First, they take a test and get some questions wrong. Then, the teacher focuses only on the mistakes for the next lesson. And as a result, they improve gradually over time. That's exactly what boosting does. It trains models sequentially. Each new model fixes the mistakes of the previous one. Now let's understand why boosting works. Well, it focuses on mistakes and improves step by step. And it is more powerful than bagging in structured data. And this is used in top ML, models like XGBoost and LightGBM. So, we've seen bagging and boosting, but what if we could blend multiple models intelligently? That's where stacking shines. Stacking, or we can say supercharged predictions. Imagine you're building a dream sports team. Instead of picking just basketball players, you take a footballer, a sprinter, a weightlifter, and a coach, each bringing their own strength. Stacking does the same. It combines different models, like logistic regression, decision trees, SVMs, and lets a meta model decide the best combination. Now, what makes stacking so powerful? First is, it learns which model works best for different cases. Second, it outperforms individual models in complex problems. And it is also used in Kaggle competitions and industry models. Now, how to choose the right ensemble method? Picking the right ensemble method is as important as applying them, and this completely depends on how your model is performing. If your model is overfitting, meaning it works well on training data but poorly on new data, then bagging is a great choice. It trains multiple models on different parts of the data and combines their results to make predictions more stable. But if your model is underfitting, meaning it's too simple and not learning enough from the data, then boosting can help. It works by training models one after another, with each new model learning from the mistakes of the previous one, making predictions more accurate. And if you already have multiple good models, but they give different results, stacking is a smart choice. It combines the predictions of these models using another model that learns how to make the best final decision. Now that we know when to use each method, let's test them on a real-world dataset. All right, now that we know what bagging, boosting, and stacking are, let's put them to the test. Imagine you're a wine expert trying to classify different wines based on their chemical properties. Sounds fancy, right? Well, instead of relying on taste and aroma, we let machine learning do the job. We'll use the wine classification dataset from scikit-learn, which contains chemical features of different types of wine. Our mission: to correctly classify each wine using bagging, boosting, and stacking and compare their performance. Let's see which one wins. Step 1. Load the dataset. We start by importing only the common libraries that will be used throughout the experiment. This makes it easier to understand each technique separately without confusion. For each method, bagging, boosting, and stacking, we will import specific libraries when needed, so you can clearly see which ones are used for what. So for now, we will import the wine data from sklearn dataset. Then we will import train test split from sklearn model selection. Now in step 2, load the data and split dataset into test and train. Here, we load and split the dataset into 80% for training and 20% for testing, so we can evaluate how well our models perform on unseen data. So for that we will, first, define X as the features, which is wine characteristics in this case, and Y as the target labels, which is wine types in this scenario. Then, we use the train test split function to divide the data into 4 parts, and that are X train and Y train for training the model, and X test and Y test for testing its accuracy. Since we are taking 80% for train and 20% for test, so our test size will be 0.2, and to ensure consistency in results, we set a random state value, which keeps the data split the same every time we run the code. Let's run it! Now here is when the magic happens. First, let's see the power of bagging. First, we will apply bagging with random forest. This is all about training multiple models on different parts of the data and averaging their predictions. We'll use random forest, a popular bagging method that trains multiple decision trees and combines their results to improve accuracy and stability. So first, we will import the library needed for bagging, which is random forest classifier from sklearn Ensemble. Now to create bagging model, we're creating and training a random forest model, which is a type of bagging technique. First, we define the model using random forest classifier, then enclosed bracket n-estimators equal to 100 and random state equal to 42. Here, the parameter n-estimators equal to 100 means the model will create 100 decision trees, where each tree makes its own prediction, and the final result is based on the majority vote. More trees generally lead to better accuracy, as the model gets multiple opinions before making a final decision, whereas the random state equal to 42 ensures that the model gives the same results every time we run the code. Next, we train the model using bagging model.fit, then in close parenthesis, X-train and Y-train, where it learns patterns from the training data. The random forest helps make predictions more reliable and accurate by preventing overfitting. Instead of just memorizing the training data, it learns useful patterns that help it perform well on new, unseen data. Let's run it and see the result. Here, after running the code, you can see the accuracy of 1 or 100%. This is coming because we have a very small data set. This does not come as 100% in large data sets, so keep this under the consideration while choosing your model. Now keep this aside and let's explore boosting with gradient boosting. This technique works by training models one after another, with each new model learning from the mistakes of the previous one. This way it keeps getting better. We'll use gradient boosting, a powerful boosting technique that corrects errors step by step. First, we import the gradient boosting classifier from scikit-learn's Ensemble module. Then we create the model using n-estimators, and we will set it to 100, which means the algorithm will train 100 small decision trees, each learning from the errors of the last. Then the learning rate equal to 0.1 determines how much each new model contributes to the final prediction. Lower values make learning slower but more precise. We also set random state equal to 42 to ensure we get consistent results each time we run the code. Next, we train the model using the .fit on X-train and Y-train. This function allows it to learn from the training data. Once trained, we evaluate its accuracy with .score on X-test and Y-test, which checks how well the model predicts the correct labels for the test data. If the accuracy is high, it means the model has learned patterns effectively and can make good predictions on new data. Gradient boosting is especially useful when a data set is complex and needs a more refined learning approach to improve accuracy. Now let's see what stacking can do. Stacking is like a machine learning dream team. Instead of relying on one technique, we combine different models and use another model called a meta model to make the final decision. Here, we'll stack a decision tree and logistic regression, then use another logistic regression model to learn the best way to combine their outputs. Before implementing stacking, we will first import the necessary libraries. We bring in stacking classifier from sklearn.ensemble, which allows us to combine multiple models. We also import logistic regression from sklearn.linear model and decision tree classifier from sklearn.tree, as these will be the models we use in our stacking process. Now let's break down what we're doing in the stacking approach. We first define our base models, which will serve as the first layer in our ensemble. A decision tree classifier, which is useful for capturing complex relationships in the data. And a logistic regression model, which is good at identifying linear patterns. These two models will make their individual predictions, and then we stack them together. The output of these models is then passed to a final estimator, which in this case is another logistic regression model. This final model learns how to best combine the predictions from the base models to make a more accurate final decision. We then train the stacking model using .fiton, xtrain, and ytrain, allowing it to learn from the training data. Once the model is trained, we evaluate it using .scoreOn xtest and ytest, which measures its accuracy on the test dataset. Simple, isn't it? Here, the key advantage of stacking is that it leverages the strengths of multiple models. Since different models may learn different aspects of the data, stacking helps improve overall performance by allowing a final model to learn the best way to combine their predictions. After running all three models, we can see clear differences in their accuracy. Random forest or bagging performed best, reaching nearly 100% accuracy thanks to its ensemble of decision trees reducing overfitting. Logistic regression or boosting, while simple and fast, achieved around 94% accuracy, struggling slightly with complex patterns. Stacking, which combines multiple models, performed slightly better at 97%, leveraging both decision trees and logistic regression for improved predictions. While random forest was the most accurate, stacking provided a balanced approach, and logistic regression remained the simplest choice. So your model selection depends on whether you prioritize accuracy, interpretability, or training speed. All right, we've covered a lot today. We explored bagging, boosting, and stacking, saw how they work, and even compared them with a hands-on example. By now, you should have a solid understanding of how these powerful ensemble techniques help improve model accuracy and performance. But learning doesn't stop here. If you found this helpful, hit that like button and subscribe for more hands-on machine learning tutorials. Also, let me know in the comments, which Ensemble method are you most excited to try? And hey, if you want to dive deeper into real-world machine learning projects, stick around because we have more exciting content coming your way. See you in the next one.